So in this video I'm going to discuss the definition of the determinant of a matrix. So this video is going to appear in the playlist on vectors and matrices. And the spirit of this video is it's going to be a maths video rather than a pure maths video. And what I mean by that is that we're just going to be looking at real matrices, so matrices where the entries are real numbers, rather than if we were doing this from a pure maths perspective, we'd be looking at matrices where the entries are from some abstract field. So we're going to stick with the familiar and arguably the most useful case. So let's begin then. So determinants only exist for square matrices. So we're mainly going to be looking at 2 by 2 and 3 by 3 matrices. However, what I'm going to say will apply also for 4 by 4, 5 by 5, and indeed n by n matrices. And the way I'm going to do this is I'm going to write down the definition for the determinant of a 1 by 1, 2 by 2, and 3 by 3 matrices and talk you through the pattern behind it, and then we'll see how this pattern generalizes to the n by n case. So firstly, 1 by 1 is not very interesting. So 1 by 1 matrices only have one entry, which I'll call A11, and I don't know why I've drawn a equal sign. The determinant of a 1 by 1 matrix is just that entry that's inside it, A11. So we can't really see much of a pattern from just that. So we'll go up to the next one. So 2 by 2, and I've already made another mistake. So A11, A12, A21, A22. So here we can actually discuss something more interesting. Now, I'm assuming that most of the people watching this video will have seen the definitions for the determinant of a 2 by 2 matrix and a 3 by 3 matrix before, and will have computed some examples before. So the answer for the determinant of a 2 by 2 matrix is that it's A11 times A22 minus A21 times A12. Now, we can discuss the pattern here. This is what you do to find the determinant of a matrix. You are looking at adding a bunch of products together where the products are entries in the matrix, and each one of the products has to contain an entry from every single one of the rows and every single one of the columns, and can only contain one entry from each row and each column. So you can't have two entries from the same row or from the same column appearing. That means that there are only a certain number of possible products, and these are the only two in the case of a 2 by 2 matrix. So you've got this entry, A11, so that uses up the first row and uses up the first column, so you can't have any more entries in the product from the first row or the first column. So that means there's only one other entry to product it with, which is A22, which is what we've got here, A11 times A22, and you've seen we've got both rows represented here and both columns represented here, and they're only represented once, so that's absolutely perfect. And then the other possibility is here. This is the sort of off-diagonal option. So the way you can methodically think about this is we're only allowed one entry from the first row, so we might as well just go through the first row and use the different options. So we've used that one up, that's done. That's the only product that comes from this one. Now we're moving on to this one as our representative from the first row. So that row is used up, that column is used up, so the only thing it can be multiplied by is A21, and that works perfectly. We've now got one representative from row 2, one representative from row 1, one representative from column 1, and one representative from column 2. So each column, each row is represented, and both of them aren't over-represented. So that's in essence what you're doing. You're taking all these products of things where you've got one representative from each row and each column, and you're adding them together, although it's not quite that simple, unfortunately. As you can see, there is this nightmare. This is the bit that actually makes this complicated. It would be really simple otherwise. The minus. So in front of these products, you're either going to have a +1 or a -1. What determines that? It's about whether this permutation of the indices here is odd or even. So this one here is the perfect case where the indices are perfectly aligned with one another. 1 is together with 1, 2 is together with 2. Here you can see that it's not perfect. Instead, you've got 2 with 1 and 1 with 2. So what you have to ask is how many switches, how many transpositions would it take to put them into the perfect order? And we'll go through this a lot more. In fact, the main bulk of this video is going to be discussing the parity of the products that we're dealing with, whether they have a plus or a minus in front of them. But what you really can think about doing is we could make a switch here. We could switch the 1 here and the 2 here, and that would make it perfect. The 2 1s would then be together and the 2 2s would be together. So it only takes one switch to make this mismatched indices perfect. And 1 is an odd number, so this is an odd permutation. So it needs a minus sign in front of it. Whereas this takes 0 switches to make it correct. 0 is even, so it has a plus in front of it. In addition, you could imagine doing a switch and then doing the switch back again. So you could say, we could switch 1 and 2 here. Oh, but that actually messes it up. You know, that makes it from perfect to wrong. So we'd then have to do that switch again. So we'd have to do 2 switches to get it perfect. Therefore, it's even. And we'll discuss this further, but parity of permutations is a massive topic. Well, it's not a massive topic, but it's a beautiful topic. It's a topic in group theory. I have a video on parity of permutations in my playlist on group theory, and in that video I proved to you that it is a well-defined concept, i.e. if you have a certain permutation, that no matter how you break it down into transpositions, you will always either get odd or even. So for an odd permutation, you will get odd number of transpositions, or if it's an even permutation, you will always get an even number of transpositions. And I'm not going to repeat that proof in this video because it took about 30 minutes, I think, that entire video to do that proof. It's a beautiful proof, but please be aware of the fact that parity of permutations is a well-defined concept. It's really essential to understanding what we're going to do here. I will talk more about it, but I won't go into the full proof that parity is well defined in this video. It would make it too long. So let's continue on up to the 3x3 case, and this is where the pattern is really going to take off. So A11, A12, A13, A21, A22, A23, A31, A32, A33. So the same thing is going to apply. We're going to be adding together a whole bunch of products where the products have to contain one entry from each row and each column and only one representative. You can't have duplicates. So for example, up here we couldn't have the product A11 with A21. This was not allowed. A11, A21 was useless. 1 because the column 1 appears twice, and 2 because the column 2 doesn't appear at all. But I suppose you could have considered the product this, A11, A21, A22. That would solve the issue that the column 2 never appears. But here it's not the case that each column only appears once, and indeed it's not the case that each row only appears once. Row 2 is appearing with 2 representatives here, so this isn't allowed. That's why for the 2x2 case the products consist of just 2 elements, because that's how you get a representative from each row and then each column appearing just once, but at least once, because we've got 2 rows and 2 columns. And in the 1x1 case, this is the only product you can have, and it's a product of just one thing. So the products are going to be the size of the matrix. If it's an n by n matrix, the products are going to be of n things. For this 3x3 matrix, the products are going to be of 3 things. So let's work through all the possible products here. So again, the methodical way of doing it is just to work through row 1. So we'll start with this entry as our choice of representative from row 1. So A11. That uses up row 1 and column 1, so we've then only got these 4 options. Let's pick this one here. So we'll have A22 as our representative from row 2 and column 2. So now we've used row 1, we've used row 2, We've used column 1 and we've used column 2, so that means there's only one option, which is A33. So that's a beautiful product that obeys our requirements. And as I say, we're going to be adding, there are going to be other products, we're going to be adding them together, and one of the things we have to think about is whether we're going to put a +1 or a -1 in front of it. This one is obviously the perfect case where you don't need to make any switches to get the indices beautifully aligned with one another. So it's going to have a +1 in front of it. It's an even permutation product. Let's continue on. So there was another option for A11, so we'll stick with A11 here. So that's used up row 1 and column 1, but instead of picking A22 here as our representative from row 2, there was another option for what we could have picked for the representative of row 2, which is A23. So let's pick that one this time. So now row 1 and column 1 have gone, row 2 and column 3 have now gone, so that means there's only one option now, which is A32. So that is another possible product here, and you can see that each row is appearing once and each column is appearing once. Beautiful. Now, this comes into question now. Should I have put a plus there or should it be a minus? And hopefully, from what I've said already, you can work this out for yourself. To make this, to make the indices perfectly aligned for this product, we just need to make one switch. Switch this one with this one. Switch the one that's in position 2 here with this one that's in position 3, and that will make it perfect. So that is going to be an odd permutation then. It requires one transposition to make it. 1 is an odd number, so we need to put a minus in front of there. So let's get rid of that plus and put minus there. So those are the two options where we pick A11 as our representative from row 1. Let's now move on and pick A12 as our representative from row 2. Oh, sorry, row 1. So that gets rid of row 1 and column 2. So I have A12. So this is gone, this is gone. So we've just got these four things as options. So from row 2, let's try putting A21 in. So A21 can be our representative from row 2. That gets rid of row 2 and column 1. So then the only option then is A33. And you can see that's another product that satisfies our criteria of having one representative from each row and indeed one representative from each column. Lovely. We then just need to think about, should it have a plus or a minus in front of it? Well, how many permutations do we need to make? How many transpositions do we need to make? Switches. Transposition just means switches. It's a switching permutation. A 2 cycle. We just need to switch this one and this one. So the thing that is in position 1, if you like, with the thing that's in position 2. So it's going to be another odd permutation, so it needs a minus in front of it. Let's carry on. So again, we'll pick this as our representative from row 1, and this time instead of picking this as our representative from row 2, we'll pick the other option, which is A23. So again, I'll put a temporary plus there, and we'll think about it more later. So A12, A23, so that uses up row 1, row 2, column 2, and column 3, so the only option is then A31. So that's another perfectly decent product. One representative from each row, one representative from each column. Does that need a plus or a minus sign in front of it? Well, this one's actually an interesting one to think about because the indexes here are really mismatched. So we'd actually have to make 2 transpositions to make this right. So we'd have to switch 1 and 2 here. So switch the thing in position 1, if you like, with the thing that's in position 3. And then that still won't be good. That's made these 2 aligned, but 2 is now here. So we need to then switch the thing in position 2 with the thing in position 3, and then that will make everything right. So 2 transpositions are required, and therefore 2 is an even number. So the plus is actually correct here. It is an even permutation product that we've got here. So let's continue on. So the final option, that completes all the options for A12. Let's now do A13. So plus A13. A13 uses up row 1 and column 3. Then we've got these 2 options for row 2. Let's pick A21. A21 uses up row 2 and column 1, so that means that this is then the only option. So A32. And is that going to be an odd or an even one? Well, let's think about this. Is another interesting one here. It's similar to this, where we're going to have to make two transpositions. So if we swap these two around, so the thing in position 1 with the thing in position 2, that'll bring 1 in here, and 3 will then be in there, and then we'll have to then switch the thing in position 2 with the thing in position 3 to bring all the numbers into their correct positions. So that's two transpositions. 2 is an even number, so it's an even permutation product here. And then finally, the final one, which is plus A13 again. And we're going to pick this one now as our representative from row 2, so A22. So that's used up row 1, row 2, column 2, and therefore we need this, A31. And you can see that that just needs one switch to make it correct. So it's going to need a minus sign in front there. So those 6 products that we've got here are the only 6 products you can have that satisfy our criteria of having one representative from each row and each column, and only one representative from each row and each column. So the products consist therefore of 3 things, and then all you have to do is add them all together, but not quite. You have to remember to stick plus 1s in front of the even permutation ones and minus 1s in front of the odd permutation ones. And that will then give you the determinant of a 3 by 3 matrix. And then this pattern generalizes. For the 4 by 4 case, you'll have products of 4 things, and again you'll be looking at what parity the permutation is that corresponds with this product, as to whether it's an odd or an even permutation. So if I just give you an example, so if we imagine having this 4 by 4 matrix, and I won't write it all out. So we've got A11 up here, A14 here, A41 here, A44 here. So if we imagine one of the products that's going to appear here, so if we have A41, let's say, and then we can have A32, which other ones do we need? 1, 4, and then A2 is the missing one there, 3. So the way I worked that out is I was just making sure that each row appears once and each column appears once. So that is going to be a valid product that's going to appear in this great big sum that's going to make the determinant. All we need to know is, does it need a plus 1 or does it need a minus 1 in this front position? And to do that, we just need to think about how many switches do we need to make all the indexes correct. So of course we're going to have to switch these two. So that'll bring the 4 here, that'll bring the 1 here, and then we're going to need to switch these two as well. So that's 2 transpositions to make it correct, so it's therefore an even permutation, so this one would have a plus in front of it. So that shows how this definition is going to generalize to the 4 by 4 case, and I hope you can imagine how it will generalize to the 5 by 5 case, 6 by 6 case, indeed the n by n case. You're just going to have all of these products added together, but remember that you need to put plus or minus signs in front of each of the products depending on whether they are odd or even. So what I want to do now is discuss this concept of parity further. In particular, what I want to explain to you is how this concept of making switches here, it is completely isomorphic to the theory of permutations in group theory. I want to show you how this is captured completely by group theory, and how the theory of parity of permutations in group theory therefore extends over to us making these switches like so. In particular, the fact that parity is well defined. So if I have an even number of switches making this perfect, and I have some other combination of switches that makes it perfect, that the number of switches that that other combination will have is also going to be even. i.e. you're never going to be able to find an odd number of switches that is going to make this particular one perfect, because it is an even permutation. So I want to look then at how I can write this in terms of permutation notation in group theory. So we'll stick with this same example that we've got here, and what I'm actually going to do to illustrate this is I'm going to rewrite this so that it's in order as far as the first index is concerned. So I'm going to rewrite this as A14, A23, A32, A41. So that's the exact same product, but now the first index is beautifully in order. Of course, the second index is garbage, it's completely out of order, but the first index is in order. And then what I'm trying to do with my switches here is get it so that it looks like this: A11, A22, A33, A44. That's what I'm effectively trying to do. So let's now think about what permutation in terms of group theory captures this. And then we'll think about splitting that permutation into just transposition permutations, two-cycle permutations. And we'll show how it's then completely analogous to what we're doing here in terms of switching, and therefore how the theory of parity for the permutations in group theory corresponds over to our switching here. So let's call this then position 1, because as far as index 1 is concerned, that is position 1. This position 2, this position 3, and this position 4. And let's draw a permutation where these numbers here are now referring to the positions. So if we switch 1 and 2, that means switch whatever is in position 1 with whatever is in position 2. So 1, 2, 3, 4. So the overall thing that we are trying to do is we want the thing in position 1 to go to the thing in position 4. So the overall permutation we're trying to achieve will have the thing in position 1 going to the thing in position 4, because 4's here, so we want it to go into position 4. The thing in position 2 is 3 at the moment, so we want it to be sent to the thing in position 3. So thing in position 2 needs to go to the thing in position 3. Likewise, the thing in position 3 is 2, so it needs to go to the thing in position 2. And the thing in position 4 at the moment is 1, so it needs to go to the thing in position 1. So this is how you would capture the permutation that we are overall trying to make to turn this into our perfect thing here. We can therefore split it into decompose this permutation in group theory. So this is written now in group theory notation here. Some more group theory notation for this is it's obviously composed of two transpositions, 1, 4, 2, 3. It doesn't matter which order you do them in. So in cycle notation, we would write this like so. This is the transposition of 1 and 4. This is the transposition of 2 and 3. And then composing them together, you just write them next to each other like this, and it doesn't matter which way round they go because they commute. Drawing it actually out, this would be the decomposition into those two transpositions. So you could swap 2 and 3 first, which would correspond to this one here. And then you could swap the thing in positions 1 and 4. And it is important to remember that we're talking about switching the positions rather than switching the actual numbers. That is potentially a point of confusion here. So this is capturing, swapping whatever is now in those positions. So this would be the decomposition into transpositions in terms of group theory notation here. And you can see that it's split into two transpositions, so it would therefore be an even transposition. And an even permutation rather. And hopefully you agree that what we've got over here written in terms of group theory transpositions corresponds to what we want to intuitively do here in terms of switches. So this corresponds to switching what's in position 2 with what's in position 3, which of course will send this 3 here to position 3 because it's in position 2. So they'll go to position 3, and this 2 that's in position 3 will then go to position 2. So that will get the 2 and the 3 in the correct position. And then what we're doing is switching what's in position 1 with what's in position 4. So this is in position 1, so it's going to position 4. And then this is in position 4, so it's going to what's in position 4. So again, to stress that this corresponds to moving what's in a certain position. These labels here are labeling the positions rather than these actual numbers. So hopefully you can appreciate that this bit of group theory here does correspond to what we're intuitively doing in terms of switches here. And the reason I'm going into this is because as I previously said, I have a video in the playlist on group theory where we study group theoretic permutations, and we see how the concept of parity of a permutation is well defined. So if you take this permutation here, it is either even or odd. And if you take any other breakdown into transpositions, you will always get the same answer as you got for the first one. So taking this as an example, we could break it down into transpositions in a different way. Let me show you how we could do it in another way. So this way is going to be a bit more less efficient, and we're going to end up doing it through 4 transpositions. So I'm preparing by drawing out the domains and codomains of each of the transpositions. So let's do this then. So we can start by doing, let's do 1 and 2, let's say, and then let's send 1 overall to the correct thing. So we'll send it to 4 down there. And now let's think about what else needs to happen. 2, oh, well, we haven't finished. So I should draw these other ones remain in the same positions. Let's get 1 going to the correct, no, 1 already goes to the correct thing, sorry. Let's get 2 going to the correct thing now. So 2 needs to go to 3. So I think if we put this transposition in now, that will send 2 overall to 3. So you can see 2 is going to go to 3. So we've got 1 going to the correct thing, 2 going to the correct thing. Now let's just look at what 3 is going to. It's going to 1. So if we get it going to the correct thing, which is 2, then I think we should be done. So we just need to then permute 1 and 2. So my belief is that, my hope is that that composition of transpositions also gives this permutation. Let's just check that. So 1 goes to 4, that's correct. 2 goes to 3, that's correct. 3 goes to 2, that's correct. 4 goes to 1, that's correct. Excellent. So it's all fine. This is another breakdown of this into transpositions, a less efficient one than this, but another one nonetheless. And you'll note, excuse me, that even though this contains a different number of transpositions to this one, so this one up here contained 2 transpositions, this one contains 4 transpositions, whether it is odd or even remains the same, and in this case it is even. So you could find other breakdowns into transpositions that contain 6 transpositions or 8 transpositions or 10 transpositions. What you could not find is a breakdown into 3 transpositions or a breakdown into 5 transpositions, because they just don't exist for this one because it's an even permutation. Likewise, if you had an odd permutation, so for instance if we had, let's say, a 3 cycle, so we had a permutation, well actually a 3 cycle is an even permutation. Let's take a 4 cycle, which is an odd permutation. So if we had something like this, 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 goes to 1, this is an odd permutation. So if you break that down into transpositions, I'll show you one of the breakdowns, you'll always get an odd number of transpositions, and you will never be able to find a breakdown that gives you an even number of transpositions. So if we do 1, 2 firstly, and keep 3, 4 the same, that gets 1 into the correct position. Let's now get 2 into the correct position. So 2 wants to go to 3, so we need to swap what's in position 1 and what's in position 3. That's got 2 going to the right thing. 3 is now going to 1. 3 shouldn't be going to 1. 3 should be going to 4, so let's swap 1 and 4. And that composition of transpositions should now be correct. So 1 goes to 2, excellent. 2 goes to 3, 3 goes to 4, and then 4 goes to 1, excellent. So that's 3 transpositions making that up. You could find other decompositions of this into 5 transpositions, into 7 transpositions, into 9 transpositions, but they will always be an odd number of transpositions. You cannot find a breakdown into an even number of transpositions. Parity is well defined, and that, as I say, is something that we prove in the video on parity of a permutation in group theory, and I'm not going to repeat the proof here. The reason that we've gone into all of this is that because we now appreciate that we have this beautiful correspondence between these switches here and these permutations in group theory, we can now conclude that the number of switches here, whether it is odd or even, is well defined, and therefore whether I want a plus or a minus in front of my product is well defined. So that was the point of all of that discussion. Before we end this video, there is one further thing that I would like to discuss, because I'm hoping to make a subsequent video in which I talk about Laplace expansion and why all of the different Laplace expansions all give the same value, and they give the value of this determinant defined as I've just gone through. And what will massively help us in that quest, in that video, is a further discussion of parity at the moment. And that is to say that we've always thought about switching the second index around here, performing these switches as the second index. Here, when we were talking about correspondence into group theoretic permutations, we talked about, permutations of the second index. But you could have done it all the same with the first index. And what I want to show you now is how the answer that you would get if you did it with the first index instead of the second index is the same. So let's again take this example. This is kind of a simple example. I could have made a more complex example. I could have had it where it was an odd permutation, that there was a full 4 cycle in terms of the group theoretic permutation. Instead, it's just a composition of 2 transpositions. So let's just write down these numbers: 4, 1, 3, 2, 1, 4, 2, 3. And now to make them perfect, you have to do these 2 switches. You have to switch those 2, and you have to switch those 2. That was in terms of switching the second of the 2 indices. What we can now do is imagine switching instead the first index, and it's completely and utterly in correspondence. So what I can now do is just imagine switching those 2 instead, and you'll get the same result. You'll get 1 and 1 being matched up. You'll get 4 and 4 being matched up. In this one, if you switch 3 and 2, you again get the exact same result. So you've got 3 and 3 now matched up and 2 and 2 matched up. Okay, the 3 and 3 is now down here and the 2 and 2 is up here, whereas up here it would have been the 3 and 3 up here and the 2 and 2 down here, but the result is overall the same. So what I'm trying to show you here is that when you're thinking about switching the second index, there is a corresponding maneuver that you could have made with the first index that would have resulted in overall the same endpoint. Therefore, if you think in terms of switching the first index, you're going to get the exact same answer as to whether you should have a plus or a minus here, because any switches that you do in terms of the second index have corresponding switches in terms of the first index, and any switches that you do in terms of the first index have a corresponding switches in terms of the second index. So if this one is well defined as to whether it's going to be even or odd, then these are going to also have to be well defined, and they're going to have the same answer. You couldn't suddenly come up with a switching in terms of the first index here that was odd. Imagine that was the case. Imagine I came up with a switching where we're switching the first index here, where we perform an odd number of switches and make this correct. Well, I would then be able to come up with the corresponding switches over here. I'd just be able to switch over to thinking about switches of the second index. There's a corresponding one over here, just like I've shown you here. So I'd then be able to have a switching in terms of the second index, which has an odd number of switches that would make it perfect, which I've just convinced you, hopefully, through this group theory argument we can't do. So overall, you can either think about switching in terms of the first index or the second index. It doesn't matter. You're always going to get the same answer as to whether it requires an even or an odd number of switches, and therefore you're going to get the same answer for whether you need a +1 or a -1. I'd just like to do a more complicated example, because this one is really beautifully simple when we've just got these 2. It's really obvious how it corresponds here, but in the general case it's more complicated. So if I do a more complicated example, let's take A41, A34, A23, and A1, what's the final one, 2. I think that should be more complicated. I think this is suddenly going to be more involved than the previous one. Yes, this looks good. So if we think about what this looks like in terms of group theory, we can think about putting them into order. No, this is fine. For the first index, it's obviously got an incredible pattern. My brain was doing something when it came up with this. So I've put them in order for the first index, and this is what it looks like. So in terms of the permutation that I need to fix, this is position 1, this is position 2, this is position 3, this is position 4. So the corresponding permutation in group theory would be a 4 cycle. So I want the thing in position 1 to be sent to the thing in position 2. I want the thing in position 2 to be sent to the thing in position 3. I want thing in position 3 to go to the thing in position 4, and I want the thing in position 4, which is a 1, to come back to position 1 where it belongs. So it's a 4 cycle, so it's a odd permutation. Now, the purpose of this wasn't to go back through the group theory. The purpose was, again, to look at this correspondence in terms of making switches in terms of the first index instead. So let's write these numbers out. We've got 4, 1, 3, 4, 2, 3, 1, 2. So if we were making switches, let's do firstly the second index. We could swap those two around there. So effectively we're swapping the thing in position 2 with the thing in position 1, because remember that's how we're labelling the positions here in terms of what the first index is. That will bring the two 2's together. Then we'll have 3 over here, so let's then swap these two around. So the thing in position 3 swapping with the thing in position 1, which will bring the 3 into the correct position, and then you've got the 4 now in position 1, and then we can do a switch of the thing in position 4 with the thing in position 1 here, and that will bring 4 here and 1 here. So this was our first, second, and third. And what I'm trying to illustrate is how it's more complicated to see how there's a correspondence now, but there still is a correspondence. So if we write those numbers out again, and now think in terms of switches of the first index. So here, we're now going to switch 1 and 2 around, and this is much more complicated. So we're switching 1 and 2 around. That's the corresponding permutation here. If you switch those two around, the equivalent result is switching these two around. It produces the same two numbers at the end of it. You know, at the end of that first permutation, writing them in blue, you have 2, 2 and 1, 3. At the end of this permutation, you also have 1, 3 and 2, 2. They've just changed positions now, but you overall achieve the same thing, the same collection of numbers at the end of it. Then, our second move here was going to be to switch 2 and 4 around here, so to bring 4 in here, and the 3 was going to go up here. So again, we're trying to bring our 3 is now still over here rather than over here, and we're trying to bring this 3 into here. So the corresponding move now is to move those two around. So remember, you've got the same numbers. Each one of these transpositions, even though we've changed which index we are switching, at the end of it you have the same 4 numbers as you would if you'd done the original thing. So if we have a switch here in terms of the second index, and we have a switch here in terms of the first index, the numbers that you end up with are the same. So there is always going to be the next corresponding switch. So up here we wanted to switch 3 and 4 around. Down here we're going to switch 1 and 3 around instead. So here really that second switch is going to correspond to these two here. Although it is complicated to see that, really writing out these blue numbers helps a lot. So you'll switch those two around and you'll end up with the 2 3's together, and then you'll end up with the 1 and the 4. And then finally, of course, you will switch the 4 and the 1 there, which corresponds to our switching of the 1 and the 4 that was here. So each one of these switches has a corresponding switch over here, and it produces the exact same result in terms of the 4 numbers. So you are then able to proceed to your next switch and find the corresponding one there, and it proceeds forward. So it is more complicated to see how they correspond. That's why I wanted to do that second example. It's not as beautiful as up here where it was really pictorially obvious how the switches corresponded, but they still will correspond, is what I hope I've convinced you there. So overall, what we have seen is that for the determinant of a matrix, you want all of these products where each row and each column is represented once and only once. Therefore, for an n by n matrix, the products will have n entries in them. You add all of these possible products together. The complicated bit is you then need to put a +1 or a -1 in front of each one of them, and that depends on whether the product is odd or even. And to work out whether it is odd or even, it is all about how many switches would you have to do to get numbers in the perfect positions. And I hope I've convinced you that that is well defined. It's a group theory fact that permutations, parity of permutations is well defined, and that it does not matter if we think about switching the second index or switching the first index. The answer you'll get will overall be the same. And indeed, you could think about doing a combination of switches of the first index and switches of the second index to get everything right. Again, I hope from this argument about correspondence, you can see why that doesn't matter, because each one, whether you think about switching the second or the first index, overall results in the same collection of numbers at the end of it. And you can then proceed forward, and you can, for the next switch, you can either think of switching the second index or switching the first index. Really, the switch exists, and it doesn't really matter whether you think about it switching the first index or the second index. So before we end this video, I'd just like to introduce you to some useful notation that captures this concept that we've seen for the definition of the determinant of a matrix, and this is the Levi-Civita permutation symbol. And I've come up here because firstly we're going to look at this for the example of a 2 by 2 matrix. So here is the determinant of a 2 by 2 matrix here. So this is a brilliant symbol that captures this concept that firstly we just want products where all of the rows and all of the columns only appear once. Each appears once and only once. And two, it captures this concept of needing a plus or a -1 depending on the parity of the permutation. So the determinant then of our matrix A in the 2 by 2 case can be written as the Levi-Civita permutation symbol, which is an epsilon, ij, a1i, a2j, and that's it. That's the beautiful way of capturing this entire complicated definition. So it relies upon us knowing this, but firstly it also relies on us knowing something called the Einstein summation notation. So really, if we write this out in full, it should be sum from I is equal to 1 to 2, sum from j is equal to 1 to 2 of the Levi-Civita permutation symbol, often just called the permutation symbol, a1i, a2j. So that's it written out in full. The Einstein summation notation tells us that we can just drop writing these, and if we see a repeated index anywhere, we know that it means sum over that index, and because we're dealing with 2 by 2 matrices, each of these obviously can only take the value 1 and the value 2. If we're dealing with 3 by 3 matrices, each of the indexes would run from 1 to 3. For n by n, it would run from 1 to n. So let's write out in full what this summation is, and then I'll show you what the definition of this permutation symbol is. So firstly, actually, I'll just write its name here. So it is the Levi-Civita permutation symbol, which we'll often just call the permutation symbol. So writing the sum out in full, so let's firstly set I equal to 1, and then we need to sum from j is equal to 1 to 2. So we'll get the permutation symbol 1, 1, A, 1, 1, A2, and j is also equal to 1, so A2, 1, plus the permutation symbol, and I is still 1, but now j is 2, so 1, 2, A1, 1, and j is 2, so A2, 2, plus the permutation symbol. Now we're going to let I equal 2, so we've got 2, and j is now 1, so because we're summing from j is equal to 1 to 2, so the first j is 1. So a 1, 2, a 2, 1, plus permutation symbol now, I is 2, j is 2, a2, sorry, that's wrong, a1, 2 it should have been, a1, 2, a2, 2. There we go, so that is just writing this full sum out. So when you see this, using the Einstein summation notation, it means this. It means sum over all values of I, sum over all values of j. Now we need to understand what this permutation symbol means. So it depends on what the values of I and j are, what the value of this is, and it will either be value 0, it's going to go 0 here, and indeed it's going to go 0 here, or it will be 1, it's going to have value 1 in this case, or it will have value minus 1, and it will have value minus 1 in this case. So 0, 0 gets rid of those two, 1 gives us this bit, a11, a22, minus 1 gives us minus that, so overall that becomes the determinant of the 2 by 2 matrix. So this is the way it works. It's 0 if I is equal to j, so that's why it's 0 in these cases, because I and j are equal to one another, and it's 1 if that permutation there is an even permutation. So again, you think about this, you think about trying to get the numbers in the correct order. So 1 and 2 here are in the correct order already, so you need to make 0 switches to get them in the right order. In the case of this one, it's not an even permutation because they're not in the right order. You have to make one switch. You have to switch the thing in the first position and the thing in the second position to get them in the correct order. So it's 1 if it's an even permutation, and it's negative 1 if it's an odd permutation. And in this case, because they're only the I and j are only running over 1 and 2, that means that it's only ever going to be even in this case, and it's only going to be odd in this case. But in the more general case, there's obviously going to be more things they can take on. And indeed, we're going to have more indexes in the 3 by 3 case and more indexes in the 4 by 4 case, as I'll show you. So let's think about why this thing up here works then. So drawing out the matrix, we've got A11, A12, A21, A22. So I've told you we want one thing and only one thing from each row and each column. So look now at this product that we've got here. This is something that's in row 1. As you vary I here, you go over the different elements in row 1. This thing here is something in row 2. As you vary j here, you range over the different elements of row 2. And then forget this for a moment, you're summing over all I and all j. So you're summing all possible products together where you've got one thing in row 1 multiplied with one thing in row 2. That's almost what we want for the determinant. The problem is that these products aren't assured to have one and only one entry from each of the columns. So if you look at all the possible products that we've got here, we've got this one here, A11, A21, that's that multiplied with that. We've got this one, that's that multiplied by that. That's this one here is then that one multiplied with that one. And this one here is that one multiplied with that one. So we have got the bits that we want for the determinant. It's this bit and this bit. But we've also got bits that are crud, you know, this bit and this bit, because these are taking elements in the same column. They might satisfy the condition of being in different rows, but they're in the same column, which means that they're not useful for the determinant. But that's how this permutation symbol takes care of that, because it's going to go to 0 whenever the I and the j, and these I and the j things here, these are the indices telling us what column these things in the product are in. So when these are the same, that means that you've got two elements here, two entries that are in the same column, so it goes to 0 in that case, annihilating these bits that we don't want. And then it gets even better than that, because for the bits that we do want to survive, the bits where we do have entries from each one of the columns, it's going to put the correct sign in front of them. It's going to put the either +1 or the -1 that we need. And the reason for that is, you see how cleverly I've done this. I've made the indexes here appear in the same order in the subscript for the permutation symbol here. So I've put them in order as far as the first subscript, the first index, is concerned. So the order that they appear here is going to be the same as the order they appear here. So the number of switches I need to make over here to get them in the perfect order as far as the product is concerned corresponds to the number of switches I need to make here to get these numbers in the correct order. So, for example, here they appear in the correct order, just as over here this is correct as far as my product is concerned. Here, where I need to make one switch in order to make them make the indexes analogous to one another, in line with one another, here it corresponds to needing to make one switch to get the numbers in the correct order, and that's because I have chosen the indices, or I've arranged the indices in this corresponding way. So when you have epsilon 2, 1, this is going to be -1 because the indexes are the wrong way round. They need a switch, a single transposition, to get them in the correct order, and that corresponds to the switch here that is needed. So it's very, very beautiful, this notation. Let me show you how it now generalizes to 3 dimensions, and then you'll understand how it can generalize to even higher, or 3 by 3 matrices, and then you'll understand how it can transfer to n by n matrices. So now for a 3 by 3 matrix, the permutation symbol is now going to need 3 indexes. So we're going to need ijk, and it will be a1i, a2j, a3k. So again, if we draw out our matrix, so here's the 3 by 3 matrix, a21, a31, a12, a22, a32, a13, a23, a33. So here what we have is 1 entry from row 1, 1 entry from row 2, and 1 entry from row 3. So summing over I, j, and k now over all their values, so all of them vary from 1 to 3, that's going to give us every possible product where you pick 1 entry from this row and product it with 1 entry from this row and product it with 1 entry from this row. So it's going to give us far too many products, but the permutation symbol is going to get rid of most of them. So this is going to become 0 whenever any 2 of the numbers here are the same, which corresponds to 2 of the entries here being in the same column. So if I is equal to j, it will go to 0. If j is equal to k, it will go to 0. Or if I is equal to k, any of those happen, it will immediately go to 0 to get rid of that product. If none of these are the case, then it will correspond to us having picked good entries here where they're all in separate columns. And then it will go to +1 if the permutation here, so if these numbers, if the number of switches you need to make to get them in order is even, it's an even permutation, it will be +1, and then if it's, and that will correspond to us needing to make an even number of switches to get them in the perfect arrangements here, or it'll be -1 if the number of switches you need to make to get these numbers in order is going to be an odd number, which corresponds then to having to make an odd number of switches here. So that is then the permutation symbol for 3 by 3 matrices, and I hope you appreciate how that's a beautiful notation for capturing what we have defined to be the determinant here. For higher matrices, so if you're dealing with 4 by 4 matrices, it gets complicated because of course you're going to have to make the permutation symbol have more and more indices, so we might need I, j, k, and then l, and then we'll have a1i, a2j, a3k, a4l, where you need to sum over I, j, k, l from 1 to 4 in all 4 cases. And then for the n by n case, it gets even more complicated. We're going to have to actually subscript the indices now. So if we're dealing with an n by n case, det a would equal, we now need n indexes, so we'll call them I1 the first index, I2 the second index, all the way up to the nth index. And then we'll need A1 1i1 times a2i2 all the way up to an in, and that will then capture the pattern. And again, this will equal 0 whenever any of the two numbers that appear in this subscript are equal to one another, because that corresponds to two of the entries here being in the same column, and it will equal +1 in the case that these are all different, and to get them in the correct order, it's an even number of switches you need to make, and it will equal -1 if, to get them in the correct order, you need to make an odd number of switches. So I hope that's clear. Thank you for watching. We will end the video here. Do go to the playlist on vectors and matrices, because I'm going to make subsequent videos to this, hopefully, where I will explain the Laplace expansion, for instance, and we'll see how, from what we've studied in this video, it follows that the Laplace expansion is valid. It is going to give you the determinant, and indeed all the possible different Laplace expansions will give the same value. They will give this determinant.